Hello, my name is Richie, and today I will present to you my final year project, the Discrete Fourier Transform algorithm for the Phasor Measurement Unit. So the main motivation behind developing this project actually relates to the protection and the fast accurate measurements that are received by the Phasor Measurement Unit. So in 2003, there was a massive blackout that occurred in the United States and Canada. This blackout left 50 million people without power for 2 days. Um, because of this blackout event, which was actually caused by high branches touching the high voltage transmission lines, causing an overburden and distribution of energy across the power lines, as well as the alarm system failing. So, because the system had failed in terms of detecting the problem, operators or system operators were more or less in the dark in terms of information provided on where the disturbance had been caused. So after this event, America and Eastern Utilities launched a massive plan to place PMUs all over the electrical grids and energy sources of America. So America now has 1,500 PMUs distributed across it. This is mainly due to PMUs post-disturbance data collection, especially the data collected after this event, proved to be incredibly useful in terms of detecting where the problem occurred and why the problem occurred, and this information could then be used to receive early warning. So why use discrete Fourier transforms as a basis of analyzing or estimating a waveform? So Fourier transforms is one of the most common analytical tools for gathering waveform information. So what the Fourier transform actually does is that it converts or decomposes time signals, or sampled signals in this case, into the frequency components, or the frequencies that make up the signal. And as you can probably tell, this is incredibly useful for recreating signals, or recreating the estimated signal. Furthermore, actually, the discrete Fourier transforms are relatively low in terms of the computational cost when compared to other more complicated or complex algorithms such as the matrix pencil method, and still retains within the accuracy rates or accuracy that is dictated by the IEEE standard. So this lecture slide is just a quick formality of how we get the Fourier transform to become discrete Fourier transforms. So on the top left here, shown here, x of t, which is your signal in the continuous time frame, is compared to the reference signal, which is this exponential here, to convert it back into this frequency component. So in real life, analog or continuous signals are actually converted into samples first, using an analog to digital converter, which is what this equation represents here. So this is referred to as the discrete time Fourier transforms. However, this is not computationally possible because there is no way of counting to infinity and then summing up all those infinity numbers, or computationally. So that's why we have the second line here. So what the second line actually represents is this discrete Fourier transform, or discrete time Fourier transform here, is then converted into what we know as the discrete Fourier series. Essentially knowing that since this infinitely long signal can be actually broken up into a periodic signal, which is why it's in between the boundaries of the first sample, or n equals 0, to the last sample. So I guess the more generalized formula of this is actually the discrete Fourier transform which is shown here. So this is in case that you don't actually have a periodic signal, and you can essentially make that periodic signal, or make the signal more periodic by enclosing a window function, which is denoted here by Wn, and then normalized by this beta factor here, or b, which is essentially just the summation between n and n minus 1 for the windowing factor. So discrete Fourier transforms relying on sampling data, there tends to be two really common problems with this. One said problem is known as aliasing. So this is a misidentification of signal frequencies, or more importantly, it just means that if your signal is not sampled at a high enough rate, it can essentially cause overlapping of other signals, causing the signal to be very polluted by incorrect sampling. So this is generally fixed if you abide by the Nyquist law or theorem, where your sampling frequency should be at least 2 times the amount of your resonant frequency of your reference signal or your signal model. The other problem, which is more likely to occur because of incoherent sampling, is known as spectral leakages. So what I mean by spectral leakages and incoherent sampling relates directly to how the signal or periodic signal functions with the windowing function. So as shown here, so your general periodic signal where spectral leakages is less likely to happen, the window here contains an integer number of periods of the original signal, and as you can see here is that it perfectly lines up, meaning that there won't be too many issues in terms of estimating. However, sometimes you'll have a non-periodic signal inside the window. What that actually refers to is that there isn't an integer number of signals, an integer number of periods within the windowing function, and this can lead to repeated signals to be mismatched, causing very sharp transients. This transients can actually appear to look like there are extra signals within the windowing function, and can cause incorrect inaccuracies within your measurement. So when dealing with the spectral leakage problem, one of the simplest methods that can be done is to change the window function. Changing this window function, say for this example and for the rest of the tests, the Hanning window was found to deform the original waveform, or whatever slice of the waveform that the window had originally, deformed it in such a way that there would be less of a sharp transient between the first window and the next window and the corresponding windows afterwards. This, in terms of the accuracy, improved it significantly. However, this does come with a slight cost of the tonal energy, and what I mean by tonal energy, I mean in terms of the discrete bins that are developed from this Fourier transform, not as high as they would be if they were convoluted with a straight up rectangular window. So the main algorithm used in this project was actually based on the interpolated Fourier transforms. So what this entire algorithm was based on was using the discrete Fourier transforms, and then using that information of the highest peak bin, displayed onto the right here with this blue and red signal. The highest peak bin would be at this peak here. Using that information to recalculate or re-estimate the amplitude of the signal, the frequency of the signal, and then the phase of the signal. And so this particular method was more efficient than the fast Fourier transforms, which tend to be needless in terms of calculation of every single harmonic component, as well as was more difficult to implement onto an embedded system. However, this particular basis was not so good in terms of dealing with white noise or harmonics. When DFT is applied to a real signal, or a real sampled signal, the images that are remaining are a positive and a negative image, or in this case a real and an imaginary, that is a reflection of the real image, are created. This imaginary component is actually superimposed onto the real image, causing it to have a effect on the overall accuracy of the signal. So this entire algorithm's purpose that expands on the interpolated DFT is to remove the signal, or remove the negative image, by using the parameters received by IP DFT, using that to estimate the negative image. From there, the negative image is then subtracted or compensated from the original signal, which is this thing, which is now dotted out here. And the previous interpolated DFT algorithm is then applied to produce the frequency, the phase, and the amplitude of the signal. So as can be seen by these static results, so static results refer to non-changing instantaneouses of amplitude, the phase, or frequencies. You can clearly see that the algorithm, enhanced interpolated DFT, can handle pure signals very, very well, having total vector error of less than the standard recommendation of 1%. With large harmonics, so including the 3rd, 5th, 7th, it handles this quite well as well, as you can tell by this graph. In terms of adding white noise into harmonics, you can clearly see there is an increase in total vector error, especially at the 50 Hz signal, but is still within the standard and will still function in terms of the IEEE standard. In terms of dynamic testing, so when the amplitude, the phase, or the frequency changes depending, or as time continues, or as you're sampling, the DFT or the enhanced algorithm was not as successful with dealing these. As you can see by the total vector error of the damp signal, there seems to be quite a large spike, and the average total vector error being about 20%, which is way beyond the standard, because the standard suggests only 3% error. However, the frequency error actually falls within the lines of what is recommended. Similarly, the step-up test, so essentially midway through the test, the amplitude is augmented or modulated by a step function and increases the total amplitude midway. So this actually appeared to be quite okay in terms of the total vector error, until it hits about 54 Hz. Then it tends to spike around 20%, or spike up to 20%. However, the frequency error still falls within the standard recommended by IEEE C37.118.1 2011. So just to quickly summarize on what this final year project ended to be, the final algorithm that was used for all the testing ended to be the enhanced interpolated DFT, and it actually showed that it was very robust to white noise and harmonics and interharmonics, so it was very good for static testing. However, in terms of dynamic testing, so the damp signal and the step up signals, it did not handle it very well. If there are future studies conducted for this project, I would recommend focusing more time towards the dynamic aspects, as these are very, very difficult to achieve correctly for DFT.